So this is the problem on the bending stress on the beam. Let us solve this problem. First we will go through it. A circular pipe of external diameter 70 mm and thickness 8 mm. Correct? Let me write the figure for the same. It's a circular pipe of external diameter 70 mm. External diameter is 70 millimeter and thickness is 8 mm. Thickness is given as 8 mm. So if the external diameter is 70 mm and the thickness is 8 mm, the internal diameter becomes 70 minus 8 millimeter minus 8 millimeter on both the sides. So which gives how much? 54 millimeter. So the internal diameter will be 54 millimeter. It's a hollow circular pipe. It's a hollow circular pipe. Now, the external diameter capital D is equal to 70 millimeter. Internal diameter thickness or thickness P is equal to 8 millimeter and internal diameter small d is equal to 70 minus 8 minus 8, which gives 54 millimeter. Okay, and it is simply supported over a span of 2.5 meter. Length of the beam is given 2.5 meter. So in terms of millimeter, it is 2500 millimeter. Okay, find the maximum concentrated load that can be applied at the center of the span. We have to find W. Okay, maximum concentrated load that can be applied at the center of the span. If the permissible stress in the tube F is given is 150 Newton per mm square. Okay, now we'll utilize the bending equation, that is M by I is equal to F by Y is equal to E by R. Okay, that E by R term is not required in this problem. We can solve the problem by using these first two equations itself. Okay, now here I is nothing but moment of inertia and Y is distance of extreme fiber from the neutral axis. F is the stress. Okay, so all the dimensions, diameter, everything is given. We can find the moment of inertia. Correct? I is equal to, it's a hollow circular section. Moment of inertia of the hollow circular section will be equal to moment of inertia of the outer circle, Mi of, or moment of inertia of outer circle minus moment of inertia of inner circle. Okay, it is the moment of inertia of the circle formula is pi d raised to 4 by 64. So pi d raised to 4 by 64 minus pi into small d raised to 4 by 64. So pi by 64, if you take common, it will be d raised to 4 minus small d raised to 4. This substitute pi by 64 into 70 to the power 4 minus 54 to the power 4. So for this answer will be I is equal to 70 to the power 4 74 then minus 74 minus 54 to the power 4 into pi divided by 64. It is 761.195 into 10 power 3. Into 10 power 3 mm to the power 4 is the moment of inertia. Okay. Now we got the moment of inertia. F is given, that is 150 Newton per mm square. F is equal to 150 Newton per mm square. Then I is nothing but distance of extreme fiber from the neutral axis. Y is equal to, so if we at the center we will get the neutral axis. Distance of extreme fiber means the distance of the periphery of the outer circle. The total die is 70 divided by 2, 35 millimeter will be distance of the neutral axis from the extreme fiber, capital D by 2, 70 by 2, which gives 35 millimeter. Okay, now I'll take this as equation number 1 and I'll rewrite this equation as equation 1 becomes m is equal to I into F by Y. Therefore, m is equal to moment of inertia, we got it as 761.195 into 10 power 3 into stress 150 divided by 35. By this we will get the moment into 150 divided by 35. So the answer is 3.262 into 10 power 6. 10 power 6 Newton millimeter. What is the question? To find maximum concentrated load W that can be applied at the center of the span. So we know that for a simply supported beam carrying a concentrated load W at center of the span, the formula is, okay, the formula for the maximum bending moment is W L by 4. We will utilize this formula now. M is equal to WL by 4. M is down, that is 3.262 into 10 power 6 is equal to W, it is unknown, into L, length of the beam is how much it is? 2500 millimeter. 2500 millimeter divided by 4. Therefore, W is equal to into 4 divided by 2500. The answer is 5 to 19 point, how much it is? 62 Newton. 62 Newton. In terms of kilonewton, the concentrated load is 5.219 kilonewton. Okay. So to this solution of this problem is over. So in the next video, I will solve this one more problem. Thank you.